So what is application? Let's talk about it. Application is literally putting or spreading a fluid, a gas, or a solid onto a surface or a substrate. For the purpose of this webinar, we're going to mostly focus on applying fluid solutions. So let's talk about how applicators work. Application is a physical process through which a substance, in our case we'll talk about liquid suspensions, are distributed across a surface. The quality of the application is affected by the morphology of the applicator, i.e. what is the capillary pull in the applicator itself, the composition of the applied substance, which means what is the surface tension of the liquid, what is the viscosity, what are the solvent types used in the liquid, substrates to which the substance is applied, again capillary pull and roughness of the surface on which we are applying the liquid, and finally the manner in which the applicator is handled by the user, which means the speed and the pressure applied by the user. So let's look at how an applicator device works. Seemingly basic designs actually require a sophisticated interplay between different types of porous components, including both reservoirs for formula storage and applicators that work together to manage formula delivery to provide the specific user experience desired by the manufacturer. An applicator delivers the liquid suspension to its surface via capillary action. Generally, the suspension is drawn from a reservoir, but in some cases, the applicator is actually dipped into the suspension and wicks it in to act as a reservoir as well as an applicator, as seen from the images here. Once the reservoir is filled with the liquid, the applicator is then pressed into the substrate, and the pores in the substrate draw the suspension in via capillary action. It is important that the surface energy of the liquid suspension is controlled so that the substrate may actually draw the liquid in or wet. So what does wetting a surface mean? Let's define wettability. Wetting is the ability of a liquid to maintain contact with a solid surface as a result of intermolecular interactions. It is directly a function of the surface energy of the solid surface which is interacting with the liquid. As you can see from this image here, on the left side you have a nearly spherical droplet of liquid sitting on a non-wettable surface, i.e. a hydrophobic surface. As you move towards the right of the image, the surface becomes more and more hydrophilic, which means it likes wetting with water, and the water droplet disperses across the surface. As I mentioned earlier, wettability is directly a function of surface energy. But what is surface energy? Surface energy is essentially the additional free energy available that molecules have at the surface of a solid due to their incomplete bonds. It is important to remember that surface morphology can affect the surface energy, which means the rougher a surface, the more surface energy available. You can see from these images again that the surface with a high surface energy is more wettable, whereas the material with low surface energy is less wettable. So let's double click a little bit more on surface energy. If you look at the image on the left side, you can imagine molecules below the surface of a material that are surrounded by other molecules. These molecules do not have any excess free energy because all their bonds are already occupied. However, molecules on the surface of the material have bonding with only the molecules below them, and there are bonds available on the top side which are free, which provide the free surface energy. When a liquid comes in contact with the material, if this free surface energy is high enough to break the surface tension of the liquid, the surface will wet out evenly. However, on the other hand side, if the surface tension on the liquid, which means the ability of the liquid droplet to keep their molecules together, is higher than the surface energy available on the surface of the material, then the droplet will not wear out the material. For example, polyethylene, PE, has a surface energy of only 35 versus water has a surface energy of 72. In that case, water does not wet out PE. Replace water with alcohol, which has only a surface energy of 24, and there you go. Alcohol can actually wet out the PE surface evenly. How do we measure surface energy? It's measured by using a parameter called the contact angle. On the right hand side, you can see a couple of images where a hydrophilic surface means one where the contact angle between the liquid and the material surface is less than 90 degrees, versus a hydrophobic surface is one where the contact angle is greater than 90 degrees. PTFE is a great example of a hydrophobic surface. PTFE has a surface energy of only 20 and it repels water really well. So why is surface energy important? Surface energy plays a key role in a phenomenon called capillary action. Sintered particle components can be designed to control the flow of fluids through capillary action. The microporous structure acts as small capillaries to move the fluid from point A to point B. What is capillary action? It is the ability of a fluid to flow in narrow spaces without the assistance or in opposition to external forces like gravity. Capillary action and inherent wettability in general occurs when the surface energy of the solid is greater than that of the liquid, which means the adhesion of the liquid to the walls is greater than the cohesive forces between the liquid molecules. The height that a liquid will travel depends on surface energy, contact angle, the density and viscosity of the liquid, and finally the radius of the tube that you can see here in the image. As you can see, the smaller the radius of the tube, which means the smaller the porosity, the greater the distance that the liquid will travel. The wider the tube, the less surface energy is available to move the liquid, and hence the less distance it will travel. In order to promote wettability of the surface or the applicator, surfactants may be added into the liquid suspension or the applicator itself. Surfactants are amphiphilic. They are compounds that contain both a group of hydrophobic and a hydrophilic group in the molecule. The head of the molecule adheres with the liquid and the tail positions away from the liquid, and it breaks the continuity of interaction between the liquid molecules and reduces surface tension. So let's look at typical problems solved by the applicators. What is the job to be done? They deliver the precise amount of liquid or solid onto a surface. They provide a reliable and leak-free liquid application. They provide a hypoallergenic and soft skin contact experience. And finally, they provide added functionalities such as antimicrobial or color change mechanisms. There are many options available for any type of situation. Our material science experts can actually help find the right option for you or even design a custom solution if needed. These solutions will depend on various parameters such as the suspension type and viscosity, the substrate type and morphology, the level of flow or the rate of flow needed to pass the suspension to the substrate, and finally the type of user experience desired. So let's look at some of the examples where the functionality of application can be used and also some of the design considerations that go behind designing the product. So let's look at some applicator examples by market. Most of these examples are from the consumer markets. However, we do have an example on the healthcare side or a medical application as well, and we are able to design any product that can be suitably used in that market as well.